So far, we have looked into the theoretical aspects of structure formation, but in order to really reach a deeper understanding of how it works, we have to turn to numerical simulations. This is a very common practice in astrophysics and many other sciences, and the reason is that many interesting problems simply do not have analytical solutions. For example, in simple Newtonian gravity, which is about as simple as it gets, we can analytically solve rigorously only a two-body problem, the Kepler problem. Add a third mass point, and there are no analytical solutions except in some very special circumstances. This was proven analytically by Poincaré 100 years ago, that there are no analytical solutions for more than two-body problem in Newtonian gravity. Now consider a galaxy with a couple hundred billion mass points of stars. Consider then hundreds of billions of galaxies in the universe. Clearly, we cannot solve that problem analytically, and we can resort to numerical simulations. Thus, numerical simulations are essential. They're not a sign of weakness. It's not just hard to do this. It's simply impossible to do it in any other way than numerically, than to simulate, using the right kind of input physics, inside a computer what Mother Nature does out there in the universe. Now, as far as the gravity part's concerned, we're in luck because the physics is relatively simple, it's well understood. We even have good understanding of the initial conditions from primordial density perturbation spectrum. Simulations of purely gravitating systems, just Newtonian gravity, nothing else, are relatively straightforward. However, if you start adding dissipative component, such as gas or radiation, things become vastly more complicated. And in fact, that's where the cutting edge of numerical simulations in astrophysics is today. And then finally, we can compare the output of numerical simulations to the actual observations of the large-scale structure. The first astrophysical simulation using n-bodies interacting gravitationally was done as early as in 1941, and not using a computer, or rather an analog computer, by Erich Holmberg. What he did is he used light bulbs and photocells, and since the intensity of the light decreases same proportion as gravity, is inverse square law, he could then measure relative acceleration from each point to each other point, compute the net accelerations, move the points, and then repeat the whole thing. A very tedious way to do it. Things really started moving on in the 1970s with the onset of modern digital computers. Here is one of the earliest simulations by Jim Peebles, the famous theoretical cosmologist. Soon enough, people are starting to add more realistic initial conditions, and here is another early simulation by Simon White. Notice that these only have few hundred particles, which is obviously vastly less than it's needed for really realistic simulation. The milestone paper was by Alar and Yuri Tumre, who did simulations of colliding disk galaxies using a lot of approximations, but with a great physical intuitions. And they already reproduced interesting morphological features like tidal distortions and tidal tails and bridges and things like that. With a small number of particles, say planets in the solar system, gravity works like a clockwork, and it's fairly simple to see what happens. But once you start having many, many bodies, new phenomena come into the play. There is a phenomenon of dynamical friction, which is when a massive body passes through a sea of other massive particles, giving away some of its kinetic energy by accelerating them all. In effect, gravitational field of all target particles acting like viscosity. So this is what Tumre and Tumre saw. And in fact, this explained many puzzling observations. We see strange-looking galaxies or pairs of galaxies, and now we understand that they are all product of galaxy collisions and galaxy mergers. More modern simulations carry out essentially the same thing and show that Tumre and Tumre pretty much got everything right. These are from Josh Barnes and his collaborators and show simple collisions of galaxy disks using more modern computations. So what are simulations used for? First, we can use them to understand the evolution of large-scale structure galaxy clustering. Then we can compare those simulations with actual observations, like redshift surveys. We can also use them to make predictions of what should be seen and help interpret things like Sinaev-Zeldovich surveys. The basic process that goes on is hierarchical merging of smaller pieces into the larger ones, and that is again something that can be studied in detail and compared to observations. Since the dark matter dominates gravitationally, by studying what happens, even with just visible components, we can understand a little more about how dark matter is distributed and thus get some clues about what it might consist of. And once dissipative effects are understood, we can then study behavior of cosmic gas, radiation, feedback by star formation, and so on. Different kinds of physics have to be put in. Obviously, first the gravity, and that's something we understand fairly well. But once we start talking about gas and dissipation, we have to put hydrodynamics, energy dissipation processes, radiation losses, feedback, and so on. So far, at least, magnetic fields do not play an important role in cosmology, but we just don't know really what happens in the very early universe and what the origin of these magnetic fields is. Possibly the most challenging at this time is the question of the radiation transfer. The photons are much smaller than in galaxies, and it's an issue of scale. So if we really need to understand how the radiation propagates through the universe, interacts with gas, then we need a very precise, more sophisticated simulations than we've been able to do until recently. But let us focus on gravitational simulations, the N-body method. Once we have sufficiently large number of particles, we can consider them as a fluid, not the gas that you know. It's a very much compressible fluid consisting of interacting particles, mostly dark matter, but also things like stars and gas and so on. To the extent that we look at gravitational interaction alone, this is a dissipationless fluid. Energy is exchanged between particles and systems of particles, but there is no net energy lost through radiation. And so there are various numerical methods that have been deployed. Direct integration of pairwise gravitational accelerations from each particle to each other one is very impractical and time-consuming. So a number of approximations have been developed that can actually convey most of the important physics and be done much faster. In some situations, like evolution of globular star clusters, where we're talking about tens or hundreds of thousands of mass points, direct simulations are actually viable. However, people do make special compute hardware that design chips that are optimized to perform gravitational N-body simulation. A group in Tokyo is in particular been producing machines like that and call them GRAPE, or for gravity pipe. Beyond that, a large class of models uses so-called particle mesh simulations, whereby collective effect of all other particles except one is smoothed into a density field, a mesh. And then you can compute interaction of that particle with a density field much faster than you would if you, say, consider all particles individually. So that reduces compute time from n squared, where n is number of particles, to n log n, which is much easier. There is another class of methods called tree methods, or hierarchical methods, which just use clever grouping of particles to compute things, again, at similar, faster pace. Which techniques is used is depending on the actual problem that's been attacked, and oftentimes many of them are used at once for different aspects of the problem. Now let's take a look at the simulation by Andrei Kravtsov of what a chunk of universe might look like as it's evolving. What's shown here is the evolution of a cubical region of the universe about 100 megaparsecs in size, and it's been rotated to show you what structure happens in 3D. Let's try it again. You can see that first dark matter condenses in smaller clumps, which then merge into ever larger ones, forming the filamentary structure that we see, the cosmic web. Now, if we look at slightly smaller scale, we can see more detail. And here we show formation of a group of galaxies, again using same thing. At the beginning, things are very smooth. Those are the initial density perturbations, very low amplitude. But then they grow, condensing into little dark halos, which keep merging into ever larger ones. Let's take a look. Very smooth at first, but soon enough things condense under their own gravity and then keep merging hierarchically into ever larger structures. Let's look at this again. And this is where you see hierarchical structure formation in action. Smaller things condensing under their own gravity, merging together to make larger ones. Here is a similar thing, but in this case, simulation of a formation of a cluster of galaxies done by John Dubinsky. Again, we start with very smooth, simple initial conditions, and you see objects condensing and merging violently with each other, making larger and larger structures in the middle. Let's take a look again. Note, this is not stars, this is dark matter. If you could see dark matter, this is what you would see.